So we're still talking about geometric sequences and partial sums here. So one of the things that you can do is, let's say that for whatever reason there's a union contract that says that you're going to start off with $20,000 salary and you have a yearly raise that's guaranteed at 5%. So I'd like to know, what is your 30-year earnings if you work that job for 30 years? These, of course, would be gross earnings. I mean, there are no taxes or anything withdrawn from them. Well, basically, that means I'm looking for S30. I'm going to add up all the year's earnings up to 30 years. And, of course, there's your A1. Now, your R, if it's a 5% increase, you've got the whole thing plus an additional 5%. So that's why you can have 1.05, because it's going to grow by 5%. So that's a 1.05 multiplier. Because basically you've got A1 plus 0.05 times A1. And then if you factor out the A1, that's where the 1.05 comes from. So anyway, so this would be 20,000 times 1 minus 1.05 to the 30th over 1 minus 1.05. And according to the book, that comes out to be $1,328,777. And that would be your lifetime earnings over this 30-year period. Now, one interesting thing that we can do with geometric series and sequences and whatnot, I guess we haven't talked about series yet, is what's called an annuity. So basically how an annuity works is you deposit a fixed amount at a given interval, like every month or every quarter. And the account earns interest. So basically, if P is the amount that you put in every month or every so often, you start off by putting in the initial amount. Then you put in a new amount, and the old amount that was in there earns interest at 1 plus the interest rate is a decimal. Well, then you put more in, and then the first amount gets interest applied to it. And then this second amount here, that was the initial amount we put in, gets more interest applied to it. I guess instead of talking about it, I should show you. So this P becomes that P, and it's that P right there, and then this P becomes that P as more interest is applied to the earlier deposits than the later deposits. Now, if you want to use a formula for this, basically you've got the nth partial sum is equal to P times 1 minus 1 plus R to the nth power over 1 minus 1 plus R. And if you simplify that, that's equal to P times, now since the bottom comes out to be negative R, I want it to be positive R. I'm going to multiply a negative 1 up top and make this 1 plus R to the nth minus 1 and turn that area, or turn that formula around. And that would be, of course, the formula if it were compounded yearly. If it's compounded more often, then the formula becomes this. So you've got the amount is equal to the amount that you deposit, or principal, I guess you could call it, times 1 plus R over N raised to the n-teeth minus 1 over r over n. And so then n would be the number of compounding periods per year, and t would be the amount of time in years. So consider this. So at age 25, we start an IRA, an individual retirement account. So we deposit $200 per month at 7.5% compounded monthly. So I want to know, how much is it worth when we retire at 65 years old? Well, first of all, the time would be 40 years because, I mean, you've got 40 years between 25 and 65. So, as a result, your amount, why did that do that? Your amount would be equal to the $200 payment times 1 plus 0.075 divided by 12 to the 12 times 40th power minus 1 over 0.075 divided by 12. Now, that comes out to be $604,000 and $765. So $604,765. Now, if you're interested in this, no pun intended, the interest on this account would be if I take that number and subtract 40 years worth of payments at $200 a piece. So 200 times 12 payments a year times 400. If I subtract that amount from the $604,000, I get $508,765, which means that in this annuity, basically, I put in a little less than $100,000 and got $500,000 in return because of the amount of interest. Now, you probably can't find one at 7.5%, but if you can find one at a decent percentage, these are really good for retirement because you don't have to put a ton in to get seemingly a ton out. All right, you just have to leave it there for a long period of time. Now, let's talk about geometric series. Now, a series is basically when you take a sequence and you add up all of the terms, and it would be an infinite sequence. So basically, I'd have A1 plus A1R plus A1R squared plus, and instead of the partial sum going up to a certain point, the series would be the sum of the whole thing. Well, what happens is, if your common ratio is bigger than 1, that means that you're going to be adding up bigger terms each time. You can clearly see that that would be an infinite sum. I mean, it would grow without bound. But if your ratio is between -1 and 1, then the things you're adding will actually shrink. So if the absolute value of r is less than 1, then r to the nth goes to 0 as n goes to infinity. So basically, you're multiplying by a smaller and smaller quantity each time you're adding. So as a result, if we let n go to infinity, and we use our formula, the sum from I equals 1 to infinity of A1 R to the I minus first, that equals A1 over 1 minus R, because that 1 minus R to the nth would be basically 1 minus 0 because of this right here. Yeah, that right there. So that's why that part drops off. So what if we consider 1/2 plus 1/4 plus 1/8 plus ... Okay? So your A1 is 1/2, and your R is 1/2 because you're multiplying by 1/2 every time. So this infinite sum would be equal to A1, which is 1/2, divided by 1 minus R, which is 1/2. So 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, so on and so forth, actually comes out to be 1. There's a really cool figure in the book. I can't show it to you. Basically, it does this. It takes a circle. And the first time, you've got this half that gets added. And then the second time, you've got this fourth that gets added. And then you've got this eighth that gets added. And then this 16th that gets added. And then this 32nd that gets added. And if you do that infinitely many times, this little slice here shrinks. And so that's how you can kind of visualize the fact that this approaches 1. Let me get rid of this ugly picture. There we go. Let's try one more of this, and then that'll be good. So we've got 3/8 minus 3/16 plus 3/32 minus 3/64, and that goes on forever. So here, A1 is 3/8, R is -1/2. So my sum, my infinite sum here, is A1 divided by 1 minus R. So that would be 3/8 divided by 3/2. The 3's cancel. And an 1/8 divided by 1/2 is a 1/4. And that's pretty darn cool.